Section: Introduction. In this section, we discuss the rise of transformers as the leading architecture in deep learning, particularly in computer vision and natural language processing. At their foundation, transformers consist of attention modules and multilayer perceptrons, MLPs. While many studies have sought to replace traditional attention mechanisms, they still rely heavily on MLPs. Surprisingly, there has been little focus on improving MLPs themselves. MLPs are made up of stacked linear layers with nonlinear activations, and they can theoretically approximate any function if enough neurons are available. However, they struggle with complex functions, such as periodic ones, especially when using ReLU-like activations. Training these networks with gradient descent can also lead to slow convergence for high-frequency components. This has prompted researchers to look for more expressive architectures than MLPs. Recently, Kolmogorov-Arnold Networks, KANs, have emerged as a promising alternative, known for their efficiency in parameters and suitability for mathematical regression tasks. KANs utilize learnable base functions for each input-output pair, often represented by B-spline curves, allowing them to model complex functions more effectively. Integrating CON layers into transformers could enhance their expressiveness and efficiency, but this integration has faced challenges. KANs have been reported to be significantly slower than MLPs, and initial applications in vision tasks have not performed as well as expected, often due to limited computational resources and scalability issues. In our preliminary experiment, we replaced MLP layers in the vision transformer, VIT, with CON layers, creating a model we call VIT plus CON. However, this straightforward substitution led to significant difficulties during ImageNet scale training, resulting in poor performance. We identified several key challenges that limit the effectiveness of KANs in large-scale applications. 1. The standard B-spline functions in KANs are not well suited for modern GPU architectures, as they require recursive computation, slowing down performance. 2. Each unique input-output pair in a CON needs its own set of parameters, leading to an exponential increase in parameters and computational overhead as the network size grows. 3. The weight initialization in KANs, while similar to MLPs, does not support the convergence needs of KANs, which can cause instability during training. To address these challenges, we introduced the Kolmogorov-Arnold Transformer, CAT, which effectively integrates KANs into transformers for large-scale training scenarios like ImageNet. We developed three key innovations. 1. We use rational functions as our base function, which improves computational efficiency and compatibility with modern GPUs. 2. We implement a group CON approach, sharing function coefficients and base functions among groups of edges to reduce computational load without sacrificing performance. 3. We apply variance-preserving initialization to maintain consistent variance in activations across layers, ensuring stability during training. By combining these solutions, we present a new variant of CON called Group Rational CON, GR-CON, which replaces the MLP in transformers. We demonstrate that GR-CON is computationally efficient and can be easily integrated into vision transformers, leading to superior performance. Our designs also allow CAT to utilize pre-trained weights from VIT models, further enhancing results. We validate CAT across various vision tasks, including image recognition, object detection, and semantic segmentation, showing that it outperforms traditional MLP-based transformers while maintaining similar computational requirements. For instance, KATB achieves 82.3% accuracy on ImageNet-1K, surpassing the performance of the same-sized VIT model by 3.1%. When initialized with pre-trained weights from VIT, performance improves to 82.7%. Our contributions are threefold. We analyze the challenges in scaling CON-based models, propose solutions for efficiency, and introduce CAT, which successfully integrates KANs into large-scale models, demonstrating superior performance compared to VIT models under similar computational constraints. Section Summary. In this section, we discuss the limitations of traditional MLPs in transformers and introduce the Kolmogorov-Arnold Transformer, CAT, which integrates group rational KANs to enhance computational efficiency and performance in large-scale tasks like ImageNet. Our approach addresses key challenges such as base function inefficiencies and weight initialization, leading to superior results compared to MLP-based models while maintaining similar computational requirements. Section: Preliminary. In this section, we discuss the Kolmogorov-Arnold representation theorem, which tells us that any continuous function with multiple variables, defined within a limited range, can be expressed as a combination of simpler continuous functions and addition. For a smooth function defined on a range from 0 to 1, we can represent it as a sum of other functions, where each of these functions is continuous. This means that a specific number of these simpler functions can accurately represent a function with multiple variables. Next, we introduce Kolmogorov-Arnold networks, KAN, which are inspired by this theorem. We define a KAN layer that learns simpler functions, acting as an activation function. A KAN network consists of multiple layers, and when we input a vector, the output is generated by combining these layers sequentially. We then examine why the original KAN struggles with scalability. We identify three main issues: the choice of base function, the presence of redundant parameters and computations, and problems with initialization. These factors make the basic version of KAN resource-heavy and challenging to implement in larger models. One specific challenge we face is that B-spline functions, used in KAN layers, are not optimized for GPU use. They are not standard functions in CUDA, leading to slower performance when implemented with PyTorch and NumPy. Additionally, the way B-splines work, where each control point only affects a small area, makes them less efficient for parallel processing on GPUs. While there are efficient methods for cubic B-splines, scaling these to higher orders is complicated. We also note that KAN's design leads to inefficiencies in parameters and computation. Unlike standard neural networks, KAN requires a unique learnable function for each input-output pair, which increases the number of parameters and computational load, especially as we expand the network. The total number of learnable parameters in KAN is significantly higher than in a typical multi-layer perceptron, MLP, making KAN more complex and harder to scale. Finally, we address the issue of weight initialization in KAN. Proper weight initialization is crucial for effective training and convergence in deep learning. The KAN paper's initialization strategy does not adhere to the principle of maintaining variance, which is essential for stability across layers. The way B-spline coefficients and weights are initialized can lead to variance instability, particularly with higher-order splines, which further complicates the training process. Section Summary. In this section, we discuss the Kolmogorov-Arnold representation theorem, which allows any multivariate continuous function to be expressed as a composition of univariate functions, and we highlight the scalability issues of Kolmogorov-Arnold networks, KAN, due to inefficient parameterization, computational demands, and improper weight initialization that hinder their application in large-scale models. We also note that the use of B-spline functions complicates GPU implementation, leading to performance challenges. Section: Kolmogorov-Arnold Transformer. In this section, we refine the design of the Kolmogorov-Arnold Transformer, CAT, to address the challenges faced by the standard KAN in large, deep neural networks. Our approach allows us to replace MLP layers with KAN layers effectively. Overall architecture: the CAT replaces the MLPs in vision transformers with KAN layers. For a 2D image, we first flatten it into a 1D sequence, apply patch embedding and positional encoding, and then process it through several CAT layers. At each layer, we perform specific operations, where the output feature sequence is denoted as the output of that layer. We replace all 2-layer MLPs with 2-layer KANs while keeping the attention layers intact. However, a simple replacement is insufficient for scalability in large models. Therefore, we introduce a special type of KAN called group rational KAN. Rational base functions. We utilize rational functions as the base function for the con layer instead of B-splines. We define the function on each edge as a ratio of two polynomials, with coefficients that we aim to learn through backpropagation. To prevent instability from poles, we use a safe PAD-A activation unit as our basis. Why use rational functions? We choose rational functions for several reasons. They are computationally efficient for large models due to their simple operations, making them suitable for parallel computing. Theoretically, they can approximate a broader range of functions, including those with sharp variations, more effectively than polynomials. Practically, rational activations have been successfully used in neural networks, enhancing expressiveness, stability, and efficiency. Implementing rational function on GPU. A key contribution of our work is the efficient implementation of rational functions on GPUs using CUDA, rather than relying on automatic differentiation in PyTorch. We compute explicit gradients for the parameters and optimize polynomial evaluations using Horner's method, which reduces the number of computations needed. This efficient implementation significantly lowers the computational cost compared to B-splines. Group con. Instead of learning a unique base function for each input-output pair, we share parameters among a group of edges, which reduces the number of parameters and computational demands. We divide the input channels into groups, sharing parameters among them. This approach contrasts with MLPs, which use non-learnable activations. Group rational con. We combine the rational function with group-wise parameters to create our group rational con, GR-con. Each group shares the parameters for the rational function, while each edge retains a unique scalar. This allows us to express the operation of GR-con in a matrix form, enabling efficient application of the rational function across grouped edges. Parameter and computation savings. The original con requires a large number of unique activation functions, but our grouping strategy reduces this to a constant number of functions, significantly lowering the parameter count. Additionally, this approach reduces computational demands, as each input channel computes the activation function once, shared across all output channels, leading to substantial savings in computation. We summarize the comparison of parameters and computation in a table. Section Summary. In this section, we refine the Kolmogorov-Arnold Transformer, CAT, by replacing MLP layers with group rational KANs, enhancing scalability and performance through the use of rational functions and parameter sharing among input channels. Our approach not only improves computational efficiency but also reduces the number of unique activation functions needed, leading to significant parameter and computation savings compared to traditional KANs. Section. Variance-preserving initialization. In this section, we focus on initializing the values for the parameters in our group rational con to ensure that the variance remains stable throughout the network. Our goal is to prevent the activation magnitudes from increasing or decreasing as they pass through the layers, which helps maintain stability. We adapt previous analyses to fit our con framework. For a GR-con layer, the output for each element is calculated by summing the contributions from the inputs, weighted by parameters, and adding a bias term. We assume that the inputs are independent and uniformly distributed. The weights follow a normal distribution, and we start by setting the bias to 0. We can describe the variance of the output in terms of the random variables involved. As we stack layers, we want the variance of the activations to stay consistent. The initialization of the weights and the coefficients in our rational function are linked. The form of the function affects how we set the weights. A key step is to compute the ratio of the variance of the input to the expected value of the square of the function, adjusting the weights accordingly to keep the activation scaling consistent. We first initialize the coefficients, then the weights. To simplify the process, we do this sequentially rather than sampling all parameters at once. We start by determining the coefficients so that our function aligns with established activation functions like ReLU, JELU, and Swish. Once we have these coefficients, we numerically estimate the gain, which helps us set the weights based on a normal distribution. Additionally, we can transfer weights from a pre-trained vision transformer, VIT model to our CAT model. This transfer is generally straightforward, as our CAT can mimic the structure of the VIT, except for the CON layer. For the GR-CON layer, we can still transfer weights effectively. The linear layer's weights can be directly loaded from the trained VIT, while the rational layers are initialized to behave like identity functions and to approximate the nonlinear functions used in the original model. This method allows us to efficiently initialize the GR-CON layer by cloning weights from the VIT model.